The International Classification of Diseases (ICD) coding system is a crucial task in healthcare facilities, where clinical notes are tagged with classification codes for medical diagnoses and procedures. The ICD coding problem is challenging due to noisy clinical document inputs and a long-tailed label distribution. Recent automated ICD coding efforts have improved performance by encoding medical notes and codes with additional data and knowledge bases. Inspired by the human coding process, the authors propose a two-stage decoding mechanism to predict ICD codes. This approach splits the prediction into two steps. First, predicting the parent code, and then predicting the child code based on the previous prediction. The model utilizes the hierarchical properties of the codes to deal with a smaller output space at each stage, increasing confidence in the predictions. The authors highlight the limitations of existing automated ICD coding methods, which do not reflect the human coding process. They discuss previous approaches, including rule-based methods, decision tree-based methods, and neural networks that encode medical documents using pre-trained language models or inject medical knowledge into language models. The proposed two-stage decoding mechanism is designed to alleviate the problems specific to medical coding, such as special vocabulary and a large set of labels. The authors claim that their model performs well in single model settings without external data or knowledge, as demonstrated by experiments on the public MIMICII dataset. The proposed two-stage decoding framework for ICD coding leverages the hierarchical structure of ICD codes, decoding parent and child labels in sequence. This framework consists of an encoder and a decoder, where the encoder embeds and processes the medical note using a bidirectional LSTM, and the decoder predicts parent labels first, followed by child labels conditioned on the parent labels and the document. The two-stage decoding framework is motivated by the hierarchical structure of ICD codes, where parent codes are predicted initially, and then child codes are predicted based on the parent codes in the document. This factorization allows the model to compute the prediction scores of the parent codes first and then predict the child codes, as shown in equation 1. The model architecture consists of a document encoder, a first decoding stage for parent code prediction, and a second decoding stage for child code prediction. The document encoder embeds each token in the medical note and passes the token representations to a single-layer BILSTM encoder to obtain contextual representations. The first decoding stage computes attention scores over the parent labels and the document to obtain label-specific representations, as shown in the equations for attention scores and label probabilities. This approach is simple, computationally efficient, and effective, as demonstrated by experiments on the MIMICII dataset. The proposed model outperforms models that use external knowledge and data, and requires less computing power and training time due to its reliance on LSTMs. The authors compare their proposed model with state-of-the-art models on the MIMICII dataset, specifically the Mimici Full and MIMICII 50 test sets. Their model achieves a micro F1 score of 58.4% on Mimici Full, outperforming single models without external data. The model uses a two-stage decoding process, predicting parent labels first and child labels based on predicted parents. Label-specific representations are obtained through linear transformations and element-wise products. The training objective is a sum of binary cross-entropy losses for predicting parent and child labels. Experiments are conducted on Mimici Full and MIMICII 50, using metrics like macro and micro AUC, F1 score, and the authors run their models 5 times with different random seeds, reporting average scores. The results show the author's model outperforms joint lot and is on par with MSMN, which uses external data. Ablation studies are planned to analyze the model's components further. The proposed two-stage decoding model's performance is compared to joint lot on the Mimic-E full test set, demonstrating a Mycroft 1 score improvement of nearly 1.0% in label embeddings. This model showcases computational efficiency, with a training epoch time of 1.25 hours and dev set inference time of 47 seconds on a single P100 GPU, significantly outperforming MSMN, which requires 11 hours and 99 seconds respectively. In the MIMICII 50 dataset, the proposed model achieves a Mycroft 1 score of 71.83%, surpassing joint lot and rivaling the state-of-the-art method KEPT longformer. This highlights the model's adaptability to classification problems with varying numbers of labels. An ablation study was conducted to evaluate the effectiveness of the proposed model, comparing it to joint lot on the Mimici full set. The study reveals that allowing child label representations to attend to both parent label and document representations drives performance improvements in two aspects: parent label prediction and performance on labels grouped by frequency of appearance. The results of parent label prediction are presented in Table 2, showing that the proposed model outperforms joint lot by 0.9% in macro F1, micro F1, and even when considering only the cases where both models predict parent labels correctly, the proposed model still achieves a micro F1 score of 65.5%, outperforming joint lot. The performance of the model is also analyzed by dividing medical codes into 5 groups based on their frequencies in Mimici full. Figure 2 shows that the proposed model outperforms joint lot in all groups, with the most noticeable improvements in the rare frequency group. This is attributed to the fact that the parent label space is smaller than the full label space, allowing for better representations to be learned. Overall, the proposed two-stage decoding model effectively leverages the hierarchical structure of ICD codes to decode from parent-level codes to child-level codes, demonstrating competitive results in both classification problems with a large or small number of labels. Future work involves integrating the decoder with a better document or label representation to further improve performance. This research paper delves into the limitations of the proposed approach to automate ICD-9 coding using a hierarchical label-wise attention transformer model. The study acknowledges two primary limitations. First, the evaluation performance is restricted by the choice of the MIMICII dataset, which lacks diversity and only features a fraction of all possible ICD-9 codes. Second, the ICD-9 coding system is being phased out in favor of the ICD-10 system, which has limited practical applications. The paper also provides a comprehensive review of related works, including various studies on automatic ICD coding. These include the use of multifilter residual convolutional neural networks, Lee and Yu, 2020. Explainable prediction of medical codes from clinical text, Mullenbach et al., 2018. And the application of pre-trained language models for biomedical and clinical tasks, Lewis et al., 2020. The authors emphasize the importance of addressing these limitations in future research, particularly in adapting the proposed approach to accommodate the ICD-10 system and expanding the dataset to include more diverse clinical nodes. They also suggest exploring new methodologies that can leverage the richer hierarchy of ICD-10 codes for enhanced accuracy and efficiency in medical coding. In conclusion, this paper highlights the challenges and opportunities in automating ICD coding, emphasizing the need for further development of machine learning models capable of handling complex clinical data and adapting to evolving coding systems. Clinical code prediction relies heavily on the selection of relevant features from electronic health records, EHRs, to ensure accuracy. Scherwegs et al., 2017, highlight the significance of this step. Existing approaches to ICD coding include label attention models, Vu et al., 2020, medical concept-driven attention, Wang et al., 2022, and multi-scale feature attention with structured knowledge graph propagation, Xie et al., 2019. The importance of external knowledge injection in ICD coding is also acknowledged, as demonstrated by Yang et al., 2022, and Yuan et al., 2022. Other studies have utilized interactive shared representation networks with self-distillation mechanisms, Zhou et al., 2021, and knowledge-injected prompt-based fine-tuning for multilabel few-shot ICD coding, Yang et al., 2022. This comprehensive overview of related work provides a foundation for understanding the complexities of clinical code prediction. Supplementary information is provided in the appendix, including dataset statistics for Mimici full and MIMICII 50, hyperparameter settings for the best performing model, and label frequency distribution characteristics for the ablation study.